Welcome everyone to another interesting DSA problem which is titled as Balanced Binary Tree. Let me start with the problem statement. We have to return true if the tree is balanced and false if it's unbalanced. So what is the definition of a balanced binary tree? Which tells us that for every node, any node, the height at which or the depth at which it goes left and the height which goes to the right, the difference between the absolute difference between those height for any instant of node should be less than or equal to 1. I will try to explain with the above two examples. For example, if this particular node, if you go to the left, the depth is 1. If you go to the right, you can see it is 1, and you can go even further, so it's 1. So 1 plus 1, 2. So for this particular node instance, the left depth is 1, right depth is 2, and the absolute difference between the left, which is 1, and the right one, that is 2, which will gives you 1, and this 1 is absolutely less than or equal to 1. Yes, correct. So for this particular node, it's fine, this condition is getting satisfied, and we have to check for each and every node whether this condition is getting satisfied or not. So let's do it for this node. This node, left the depth is 0, right the depth is 0, and the absolute difference of 0 minus 0 is 0. 0 is obviously less than or equal to 1. So for this node is also, it's fine. What about this node? This node, the depth is left towards 1, right towards 1. So 1 minus 1 equals 0, less than or equal to 1. Yes, for this node is also, it's absolutely fine. What about these two nodes? You can see 0, 0, 0, 0. So both these nodes, the condition gets satisfied and it's absolutely fine. Since the entire nodes of this binary tree satisfied this balanced binary tree condition, we can return a true for this particular tree. And what about the next example? If you see this particular node, go towards left. 1, 2, 3. The left depth for this particular node is 3 and the right depth is 1. So let's take the absolute difference. 3 minus 1, which is equal to 2. Is 2 less than or equal to 1? No. So this condition has been disobeyed. So at this particular stage, we don't need to check for any of the other nodes. We can just simply return false. So this is the problem statement of balanced binary tree. And how can we do that? To solve this particular problem, I would recommend you to go and see. There is one traversal method we have discussed, which is known as post order. Let me recall it. Post order traversal. In that thing, what we did left, then followed by right, then followed by the root. This was the keyword which we have followed. I would recommend go back and watch this particular problem where we have discussed post order traversal of a binary tree. So let's keep that in mind, and with that we are going to use the recursive method to solve this particular problem. So this will automatically take care of each and every possibility we need to check. So let's try to minimize this whole explanation because we need some more space to write the entire code. So let's minimize it a bit. Yeah, this works fine. Just try to start the code. So this is the class solution and everything. Class solution. I will explain each and every step while we are coding. This is the method inside the class. Define is balanced. So root is given, which is nothing but optional tree node. We just need to return a boolean expression, a true or false. Now let's use a helper function. Basically it's not a helper function, it's a recursive function we will be calling again and again. So let's name it as define height. So one argument would be the node. Initially we would be passing the root itself. So in general we can call it as node. And the one condition, whenever we ends up in a leaf, so there is no more further you can go, there you can return. Basically what we are going to do, we are going to measure the depth using this thing. That's why whenever we encounter a leaf at that point, that is nothing but if not node, we just need to return 0. This is nothing but starting point of measuring depth. Okay, we have seen the depth of a binary tree in a previous problem, so we can intuitively understand what exactly we are doing. And let's go as much as we can go towards the left. Keep in this mind of the post order traversal. So left equals height node dot left. So this will take us as left as it's possible, and we are going to use, I'm going to write one condition. This particular condition will make sense after few seconds. It is required. If left, so when are we going to assign left equal to -1? That is the doubt at this particular point is going to come. So why this statement we can see. And similarly, as you can see, post order traversal, left then followed by right. So for the right also we are going to use this thing, height node dot right. And if right equal to -1, return -1. So let me comment it out, because these two right now might be a bit ambiguous. So I will fill it, this thing. Right now let it be question mark. Why? Okay. This is nothing but this -1 will be assigned at any instance, like any instant of node, if the absolute difference between left minus right, this is the condition of the balanced binary tree, is greater than 1, that time we just need to return -1. This is called as B. Let's comment it out, and this is called balanced binary tree condition. So this particular thing is what going to assign over this particular left and right at some instances if it occurs. So that's why we need to check. This is for an early exit, that it makes sense right now. So let's go back. But if it, so what we have, but before that, the left and the right, whatever it is, we have to measure the depth. The depth is measured here. Return 1 plus maximum among left comma right. So this is whenever we have encounter a leaf, we are going to measure the depth, how far we have came across with respect to the node at the stem, like node. And what we have to do, when the balanced binary tree condition has failed, and it is guaranteed that at some point left will be assigned -1 or right will be assigned -1, whatever be the condition, like whatever be the node instance when we are going to encounter this condition, that time this particular function will exit with -1. If it's not that the case, it will be exiting with a 1 plus maximum between left and right, or whatever it is, a non-negative integer, it will exit with. So if it's exiting with a -1 number, that means this condition got violated for any node. We don't know which node, like there are multiple possibilities. That's why the recursion is going to happen here. So we just need to check that condition at the end. So this is the indentation, exact indentation. So we have to return true or false. That's nothing but we have to check the condition. So the height, the function, we are going to start with the root. If this root, this particular thing will start traversing in a post order fashion, and we'll check all the roots, all the nodes, whether the left minus right, this condition is getting satisfied or not. And if this condition is not getting, that balanced binary tree condition, this one is not getting satisfied, that means we'll return -1. If it's not equal to -1, that is true. So we need to return true when it's not equal to -1. So that's how we do it. And what is the time and space complexity? So it's guaranteed that we will be visiting each node once. So the time complexity is order of n, and the space complexity basically depends on the recursion stack, basically h, the tree height, so how far it height. And sometimes when it have an early exit, it might no need to go up to that thing, so you can call it as order of h, where h is nothing but the recursion stack or the tree height. So I hope you understood this problem statement, and thank you for listening, and I would recommend you to do a dry run that will solidify your understanding. So thank you.